homogeneous and squid. Heterogeneous will be like oil with water. If you have solid with liquid,
Salt and water.
it can also be in a squid
The powder, no?
if it's made with powder. And heterogeneous, it will be like rocks and water or salt and water.
Or
Okay.
homogenized raw milk.
Now, if you have solid and solid, for example, homogeneous, it can be cement.
Play.
Cement, you don't know which part is cal, which part is rocks. Well, rocks you may be able to do. But cement is made of cal and sand. So it's quite difficult to see where is the sand is and where is the cal. Heterogeneous, it may be, for example, M&M's. No sé cómo se hace el Y. Es lo más cercano a un Y. But those are the main, most common types of solutions that we may have. For example, we can also have liquid and gas. Homogeneous, it will be soda.
But you can see
If you shake it, you can see the bubbles. But if you don't shake it, you cannot see them.
true.
So technically, soda can also be in here because it's dependent on the movement. Okay, it's dependent on the moment that you are doing the comparison.
Bread could be solid like that.
Bread,
Like a mixture.
yes, the mixture, yes, solid and liquid. Okay, and finally, we're just missing one, which is gas with gas. And in this case, homogeneous will be like air, and heterogeneous it will be like I don't know, air and clouds. If you are if you try to stretch it, okay, because technically with air, with gases, it's quite difficult to have a mixture that you can see, the difference.
Maybe like, what was the name of the green gas?
Green gas.
Or wasn't there like a toxic gas that was of color? Yeah,
There are many.
Like pollution gas.
CO2 can also smoke.
Smoke.
Smoke can also be an example. Okay, so yes,
Can you give me another example of solid and solid?
solid and solid.
Heterogeneous.
Heterogeneous, M&M's,
Cheese with
granola, shredded cheese.
Shredded cheese.
If you combine them, you can see the parts.
like cheddar.
I put soda for both, but for example, a heterogeneous liquid and gas, it would be water when it's been condensed. You can see the gas and you can see the liquid. Steam.
Okay.
But that's not quite a mixture, you know. It's stretching it. The main ones are going to be these ones. These ones are the ones that we have more established ways to separate it. Because can you separate the gas from the soda? Yes, you can. When I was in high school, I did a project about that, and what we did is that we sunk a bottle of Coke in water, and we were shaking it, and the gas was being released, and with a balloon, we were retrieving the gas, so that it went up because of the atmospheric pressure of water. So you can, but is it a proper technique? No. Okay. So for liquid and liquid, solid and liquid, and solid and solid, we do have separation techniques. Some are going to be for homogeneous, some of them are going to be for heterogeneous. Examples. For the first one, the most common one is filtration. Filtration is to separate solids from liquids. Okay, so how does it work? Is you have a funnel with a paper, you pour in the liquid, and the solids are remaining here, and the liquids are retrieved in another part. Then we have that's solid and liquid, and this one is for solid and liquid that are heterogeneous. Okay.
True.
Another one we have
Decantation.
decantation. For decantation is for liquids, liquid to liquid solutions, but these ones they have to be heterogeneous. Why? Because you need to see where they are separated. To make a decantation, you need a decantator where you have your two liquids. Here you have water, and here you have oil. These ones are separated because of their different densities, and you make them go through a valve in which you separate them according to their densities. You let the water fall, and then you have water in the base or in the. Ah, se me fue el nombre, pasó el precipitado.
Precipitate.
No, tiene un nombre.
Beaker.
Ajá, in the beaker, and the oil is retained in the decanter. Another one, we have division, also called sieving.
With the sand and the solid, no?
Yes, these ones are solid, and
Heterogeneous.
these ones have to be heterogeneous. How does it work? You have a grid
Colander.
or yes, and these ones are separated because of size. So you have the bigger ones that are being retained.
Teacher.
on the top. Yes.
Decantation was by gravity, right?
It's separated because of the difference in density. Okay? And there you have the ones with the smaller size. Okay? So that's privation.
Condensation?
No, that's not to separate. That's to the proper or
Like
the proper technique is not condensation, it's evaporation.
evaporation.
Different boiling.
It's difference in boiling points. But this one
Solid liquid, right?
it's to separate solids from liquids,
Or liquid.
or solid from liquids. Liquids to liquids is distillation.
Distillation.
So evaporation is to separate solids from liquids, but these ones are homogeneous.
Uh-huh.
For example, if you want to separate
Salt
salt
from
from water, you boil the water, and the water is going to be released, and the salt is going to be retained at the bottom. That's how we obtain sea salt. There it is. What else? The distillation. Distillation is to separate liquids to liquid solutions or mixtures, and these ones have to be homogeneous. If you see, we left the heterogeneous behind, now we're with full homogeneous. How does it work? You have your, let's say that this is wine, okay, and you heat it up, like to maybe 60 degrees. And the alcohol is separated, and it has to be cooled down using it's a flux refrigerant. Cool.
No, pero.
60 wine.
6.
Yes, yes,
Profe, es en el que luego ponen de que para clarificar bebidas alcohólicas.
Distillation.
Yes, yes. I just let me make
A ver cuánto tiene ron y luego lo hacen.
yes.
O sea, tiene-
Many of what we call distilled drinks or hard drinks, bebidas duras o bebidas secas o bebidas destiladas, they come from a pre-fermented drink. For example, whiskey is obtained from from beer. Both are made of wheat and grains and malt. So if you make malt beer and you let it ferment, and then you take it and you distill it, you obtain whiskey. If the whiskey you distill it again, it comes from dark whiskey to clear whiskey, and that makes it. Let's say pure. It removes. It removes imperfections and sugars mainly. It retains only. Es que no vimos azúcares nosotros. There are 3 types of sugars: 1 sugar, 2 sugars, and polysugars.
Mono.
So you retain the ones with 1 sugar. So it's
glucose.
yes, you retain only glucose, and it's clearer, and it's not that it's healthier, but it's sweeter. Yes. So that's distillation.
Centrifugation.
Yes, but I think I'm missing another one.
Sedimentation.
No, that one has to do more with filtration and decantation, like the mixture of both. So it's not technical at certification. Yes, chromatography.
Ah, true.
Okay, certification is separate liquid to liquid solutions that are homogeneous. And the best example that we can have is blood.
Oh.
Actually, I want for the next semester, I want you to make blood samples.
Le
Yes.
sacamos la sangre a Ana María.
To obtain percentages of measurement. It has to be with the figures, because if we will need to talk with the infirmary and the biology class for them to make the removal of blood.
Yes, teacher, yes, yes.
Crossover. Yeah, it can be. So, you have here your centrifuge,
Pero no sé si debería abrirlo.
and how the centrifuge works is by using the
Pasar de que
centrifuge
voy a
force.
que me lleve una.
The centrifuge force, for example, we stay here in the planet because we have the gravity force that is pulling us down. The centrifugal force or centrifuge force is when you are moving around a certain edge, and there's going to be a force that is going to be pushing you to the sides. What happens with these liquids? Because the force is quite strong, whatever mixture that has been solvatized is going to rearrange itself according to its weight. So that's how when we separate blood, we obtain fat, plasma, and proteins. With plasma typically is just water. Okay. So yes, that's the other one. The final one is also liquid to liquid. It's also for homogeneous, and it's mainly to separate colors. Yes, yes. Qué bueno, malo.
Okay.
Nada. For chromatography, you use. There are many types of chromatography, and actually, chromatography extends us to a big part of chemistry that I really like, which is not to separate compounds; it's to identify molecular compounds. There is this device called HPLC, high pressure liquid chromatography. What is that? You take any sample and you take it in a syringe. That if you break that syringe, it costs 10,000 pesos. And you put it in a device. You push it in, and the device goes through a lot of lasers, which diffract the liquid because it has to be a high pressure. So it makes it not instantly, but it makes it quite fast. It's been irradiated by different lasers of different ranges of the electromagnetic spectrum, UV, infrared, and radio, I think is also. And according to those, radio. And according to the light that is re-emitted, because there has to be a lot of detectors. According to how the light is redirected, it's absorbed, and according to the different peaks that you have in that radiation, because technically everything is weight, you can see which functional groups are in your sample and which functional groups are connected to which part of the molecule, to the left or to the right, and with that you can take any sample of anything and you can say, okay, it has this, this, and this. And also there's a whole study of chromatography, of HPLC, that there's a lot of databases of pre-established samples, so that it makes it easier for you to know what is an unknown sample. It's quite exciting to use that one, but there are certain rules for you to use it, because you cannot just take the sample and push it in. You have to make some washes and stuff like that, because certain materials cannot enter in there. For example, metals. You have to remove metals. So it's mainly for organic materials.
So you remove the iron, like what if like a food has iron?
You have to make some washes and you remove it. Yes.
Probably blood.
Yes. Yes. Good. This is mainly to know known chemical compounds that are not polymers. That's another one. You shouldn't have polymers. If you have polymer, you have to depolymerize it so that it can read which is the polymer, and then you know which is the polymer.
Actually, you just extract them.
Yes, you take the polymer and you depolarize it by making some washes with acids, and you obtain the monomers. Then you extract the monomers and you inject them, and you have the value of the monomer, and then you can, by logic, know which is the polymer. So yes, the simple chromatography just to separate colors. Probably the laboratory that they gave you is that they put some, it has to be like a non-primary color, and you put it in a solution of water with alcohol, and by, ¿cómo se dice arrastre? Sí, arrastre. Dragging? Yeah, by dragging, by a dragging force, it literally drags the colors that create the one that you have. No se ve así como puntitos, pero se ve como.
Sí.
Questions?
No.
No, pues.
Yo sí.
O tal vez.
Oye, sí, yo quiero.
You can feed me.
No, you're not.
Lo vendieron. Muchas gracias. Then, okay, I will do this part spoken because it's mainly theory. Atomic structure. So, what makes the atomic structure so dependent for reactions and stuff is the periodic table. So, according on where, is located your element that you have a compound of, you can preset the possible structures that it may have. For example, if you take an element from the group 1, okay, how many electrons does it have? One.
One value.
So it's quite, it has the highest possibility for example, sodium chloride to be linked with something that has the complete opposite charge, okay, +1 and -1. Which formula, which structure will be made from here?
So,
And this is a linear structure, okay? So, how can I pre-establish this? The number of the atomic number.
equals 0. You have to.
Yes. When they are together, they should be equal to 0. And that's what gives us the different compounds, yes?
What is the name of el tema?
Atomic structure.
Okay.
So, for example, a compound with a charge of 2, it can have two ways of representation. You can have it with both electrons in one side, or you can have it as having one electron in one side and one electron in another. That gives me two types of structures. So this one can be either linear, or it could be trigonal plan. Then if we take something with 3, it can have it like this, 1, 2, and 3, or it can have it like 1, 2, and 3. Okay, this one is also going to be only trigonal, but this one is going to give me the same as this, which is going to be the boride with 2 more things. But this one can be linked with 3. This is trigonal planal. This was trigonal pyramidal. And this one was linear. Now, can boride be also linear? Yes, it can also be linear, being like this. Okay, so it all depends how you are arranging it.
Profe, y ahí podría haber un logo con.
Yes, that makes it linear. That's what makes it linear. Also the presence of triple bonds. So yes, now the important ones are going to be the ones in the group 4, because carbon can have this structure. It can also have this structure. It can also have this structure, and I think I'm missing one. ¿Cuáles son cuatro? Es enlace triple. Yes. This is structure. Los triple.
Ya
Ajá.
podría haber un nitrogen para hacer un nitro.
Yes. So, according on how it is arranged, is how you can have different possible structures. Technically, this one and this one are going to be both linear. Why? Because it's as if you were having a triple bond, and here is as if you were having two double bonds. That's linear. No, this is angular. Because it does have, it's not in 180. It has a little bit more of a bending, but not too much. Some people also call this one a bend structure.
But then wasn't when you had unpaired bond? Unpaired, no? Like if all of the bonds are paired.
That's what it refers.
No, yes, but
Or you mean something like this?
yeah, like when you
Because
have
this one is going to give you a double bond and two hydrogens. This is trigonal.
No, pero.
But when
Sí,
you have
yeah,
a long
yeah.
day, I'm only one.
o sea, when you had an unpaired
Yes, but that is with that is okay. Yes, I understand. That only happens with the ones in the carbon. This is also linear or bent. It depends on the amount of hydrogens, electrons that you have. Yes. Sí, ya lo sé.
Mister,
Yes.
are you gonna see the topics of como que
SPDF. Yes.
Oof.
So.
Oh,
And
yes,
finally,
I-
this one that has the three is, if you remember,
Quantum numbers.
is the tetrahedral.
The
Okay.
Pero se
Now
fijan
there are
es
more.
que-
Yes, but those are for metals. The most common one or the most famous is the octahedral. But when can we find this thing? When we have large metals or heavy metals
lattices.
with high lattices. Okay? It's more for you to identify than to draw them. Okay? Questions?
Can you
Yes.
go back to the boron?
Yes. Les voy a pasar el documento.
Okay. So it only has trigonal planar, linear bent, and trigonal pyramidal.
Yes. Then, well, isotopes, you should know that it's an element that has a different amount of.
But I forgot how
The
to.
number.
That there were activities in which
I-
you got
Yeah,
the
you can know it
neutron.
because the case of the isotopes, how to identify an isotope without knowing the amount of electrons. For example,
the
let's say
same.
that I give you
Profe, se llama octahedral.
There were activities in which you could
Octahedral.
Different number of electrons, right?
so hydrogen has an atomic number of 1 and it has an atomic mass of 1. Okay? So if I tell you that you have a hydrogen with an atomic mass of 2, that one is an isotope. How do I know that? Because the atomic mass is the sum of protons and neutrons. And this is atomic mass. And this is the atomic number. Okay? And the atomic number is the number of electrons. Okay? So, in a normal, in a normal molecule, the number of electrons should be the same as the number of protons and the same as the number of the neutrons, because it makes it stable. But in this case, what is going to be different? The electrons are going to be the same, the protons are going to be the same, while the neutrons are going to be more. Okay? Now, technically, sin más. Okay, so if you pay a little bit of attention, you will know that technically this wouldn't make sense. Why? Because 1 plus 1
2.
shouldn't be 1, right?
Yes.
It's because actually the atomic number, this is more of an estimate. Okay, it's not a real one. Okay, you can check it with
It
any
was
other.
the
For example,
average.
chloride.
The average.
17 plus 17.
35. 4.
34. So is it the same? No.
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 Okay. We establish this more for when we have the difference in
What is
números. Sí, aquí no se los estoy dando correcto el número. O sea, tendremos que hacer el cálculo. Si la masa atómica es de 2, entonces tengo un protón más neutrones. ¿Cuántos neutrones tengo? Pues un neutrón es igual a 1, ¿no? Si neutrón sería 1. Pero no hace sentido porque pues ese es el mismo valor del original. Pero el original, busquen en internet cuántos neutrones tiene el hidrógeno normal. Pero por ejemplo el tritio, que sale en Spider-Man, es con lo que se hace el solecito de los neutrónicos. El tritio es el hidrógeno con 3 neutrones.
Ah, pues tridio. Ah.
Se puede
El
hacer
de-
la guerra.
Sí, pero es muy inestable. Está el deuterio, que es con 2 neutrones.
Deuterio.
La bomba de hidrógeno está hecha de deuterio. Y hay unas que también las hacen con tritio.
Y no había de que, me acuerdo en exámenes pasados había actividades en las que nos daban de que el average teníamos que sacar el isotope o... No me acuerdo
No
exactamente.
me nada más identificar, que sepan la definición.
Ah, ok.
Ok.
O sea, lo principal de primer semestre, o sea, de tercero del semestre pasado, va a ser pura teoría, o también va a haber ejercicios.
Nada más les voy a poner ejercicios de lo de CPDF, que es Electron Configuration.
Ah, ok.
Y en teoría de lo de Molar Mass y Avogadro's Number, porque lo vimos con.
Ah, ok. O sea, esto es chemistry, de gases.
Ah,
Ok.
sí.
Pero gases está facilísimo. Gases
Se me olvidó.
Ah, es el
súper
técnico
fácil.
fabuloso.
Profe, ¿nos va a dar las fórmulas o es de que aprendí?
Es booklet, ¿no?
Booklet.
Ay,
Pero para el
Pero había algunas que no venían.
Ya me están haciendo dudar. ¿Si era con Booklet?
Sí.
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 Pero vienen ahí, ¿no?
Nosotros tenemos el bucle.
Yo no tengo nada. Literal, de que apenas me dieron cognitive.
¿Nos pueden mandar el
Ah, de Electrical Configuration, lo de S,
Sí, es igual que
no, S.
Destruido.
Ok. Va.
Fruit.
No, ya no me gusta el
Va.
No, porque no quieren cambiar la tableta y después me lo trato de explicar como 50 veces.
Okay. Now we have bonds. Okay, so we have intramolecular.
Forces. De puentes de hidrógeno.
No, intramolecular is different than
Ah,
intermolecular.
sorry.
How can I identify them? International means outside of the nation, whereas intermolecular
Oh,
Inside
okay.
is going to be outside the molecule. Okay,
Internacional.
so the intermoleculars are the ones that you were saying. Is the hydrogen bond
The dipole.
is in between molecules. Yes. Then it's dipole.
Then it was
Ah,
Un
normal.
momento o algo así.
Dipole moment.
I was going to go to the London dispersion forces.
Ah, también.
Uh-huh. There was another one.
Sí,
Yes,
que era...
Van der Waals forces.
Ah, sí.
But the Van der Waals forces are.
I think there was a dipole.
Dipole.
It was like normal dipole and then dipole the
Induced.
one.
Ajá,
Uh-huh.
induced dipole.
The electronegativity.
Y los moment dipole.
Now, I arrange them in this way so that you have the highest polarity or the highest force to the lowest force. Okay?
Yes.
Now, the hydrogen bond, if you remember, was made with the chum. Actually, here you have to add close fluor. So the chum, or no, era chumps, ¿no?
Huh?
¿Y
Sí,
por qué
sí, no, sí, no era fósforo y azufre, ¿no? Chumps.
No.
Ah,
sí.
no, era chido.
Do not fear the ice cold beer. No.
Nosotros no habíamos hecho.
No, pero es que...
Ah, sí me acuerdo, con la fría, la Ice Cold Beer.
Ah, pero ¿qué era eso?
¿no?
No me acuerdo.
Creo que eran los dicotomic.
Ah.
Okay, so if you see
Sí me acuerdo
two
de ese,
molecules
sí,
that are being together or being put together because of the combination of hydrogen and some of the chum, that's a hydrogen bond. Dipole, has to do with
No era de que. Don't feel like
with ionic.
yodo,
Sí, los que estaban juntos, sí. Los
Pero, ¿dónde está todo?
dicotomías.
Dipole has to do with ionic bonds. Ionic bonds, let's just remember that were between metals and non-metals.
Don't feel the ice cold.
And there was another one that had to do with metals, which was the metallic bond.
I know.
Okay.
How you feel?
But the metallic bond, I put that in the top, but that doesn't mean that it's the one with the highest electronegativity.
That's ionic.
Es ionic, ¿no?
I was.
I was
Okay, why did I put it here? Because technically metallic, it can have a very high or it can have a very low. Okay? Why? Because metallic makes alloys. Okay? I just put it at the beginning, but it's outside. Okay? This one it doesn't count. It's not in the range. Okay? So after ionic we have covalent.
sharing.
Covalent polar. Covalent polar are in between non-metals and non-metals.
But
But these ones need to have a electronegativity from 1.7
Ya me acuerdo.
didn't carbon
to 0.4. What?
didn't
Non-polar.
1.7 or 1.2?
A la non-polar.
teacher
And
what was the
covalent.
name of the covalent bond on which one shared the other electron?
Porque te acercas a
Like carbon trioxide or
Sí, ¿no era de qué? Coordinate, combine.
coordination bond. Coordination bond. That's-
Eso no, no viene.
Bendito Dios.
Okay.
Dios es grande, ¿eh?
Oye,
Ok,
si
pero
la
Dios es
quiero no
grande.
recuerdo porque la vas a tirar.
Actually, the coordination should be around here. And that one and the covalent polar are in the induced dipole. Whereas the covalent non-polars,
Se coordinan.
whereas the covalent non-polars are in the non-dispersion force. Okay? Questions?
Yes.
Not really.
Was it correlation?
Digan the coordination.
Es cuando tienes, cuando el otro molecule no tiene suficientes electrones para donar, entonces uno, para prestar, entonces uno le dona sus electrones al otro para que puedan de que prestarse.
Es básicamente eso.
De carbon trioxide, ¿no? Sí.
Básicamente.
Carbon dioxide.
Es que
¿Qué es lo que ustedes? Esto lo ves en Lewis, aquí tienes el carbono está dando 2 electrones y el oxígeno va a dar también otros 2 electrones.
ahora se te dice que
Y aquí igual. Entonces, este bond es un bond de coordinación.
Can we touch tips?
Questions. Por eso es que el CO2 no es orgánico.
What was the difference?
Para que sea orgánico tiene que ser covalente.
Intermolecular.
Yes, they lend each other.
A ver, déjame te lo explico.
Se prestan electrones entre ellos.
Las intermoleculares son muy internacionales, de que afuera y de que
no,
de que
no.
Intermolecular
otras
is
con
between two molecules.
No
pero
sé.
A
intramoleculares
molecule that is ionic and another molecule that is ionic.
así. Acá es de que agarras dos.
Escuche, que la vez pasada que hizo esto no sirvió,
Agarras de que agarras dos.
Ajá.
Dos.
Or you can
De
have
que
composed
dos.
for London
Así.
dispersion, one
Por aquí es de
selection.
que no.
One that is covalent non-polar and another that is covalent non-polar. But everybody they carry out London dispersion.
Una es esto y
But the covalent non-polar is in between atoms. Okay? So intramolecular is in between atoms, intermolecular is between molecules.
Okay.
Questions?
No.
Okay?
Pero este no está
No,
hay que hacer shit, les estamos tomando foto y grabando.
That's
Porque lo vamos a ocupar por el reto. Para mañana, ahí te la encargo.
No, that's the London dispersion force.
Ya, bueno,
Hmm?
bueno.
Yes, London.
Profe, nos dijo que sí va a haber una descarga, ¿verdad?
What?
Sí va a haber descarga.
Este es
No le he hecho, no he terminado los experimentos.
de hecho, los de
Pero no le pasa y tienes que saber de los lados de qué hacer. Cristi hace esto y no te pide que.
Sí,
Basado en
colega.
la tablita.
Seguro.
Sí, no sé qué
El,
que suma todo.
que queda como, ¿cuánto conseguiste? O de que,
del elegido.
percent theoretical yield y percent
Ay,
yield.
no, esto está bien feo.
Ay, yo creo que tiene que suceder que. ¿Qué equipment podría utilizar?
Electron configuration. Why do we use the electron configuration? Is to see how the last electron or any electron of a certain molecule behaves. To see which is the position that they will have, which is the area that they will enclose, and to which side are they going, left or right. That is defined by the terms of N, M, L, and S. N is the principal number. And if you want the definition of the principal number, what does it mean? It means the size of the molecule. The larger you go, and you can see it in the periodic table, and for this I will use this one.
F minus 2 and
Okay,
E minus 1.
the atomic number n or principal, you can see it in the periods of the periodic table. These hydrogen and helium are going to be in the first size. The second size is going to be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, all of those are in the second size. The size increases the more you go down. That's why you only have 7 numbers available for the principal number. Now, that's the n. It gives you the size. Then you have L. This is called the azimuthal number.
Minus
Ya sé
three.
que tiene un nombre y es una letra y le dicen número.
Minus 3 to plus 3, no?
Asimu, what is it?
Azimuthal.
Asimu?
Azimuthal.
Fal.
Minus 3 to plus 3.
Azimuthal number?
Azimuthal number. Ya sé que es una letra que tiene nombre, le dicen número, pero es una letra. Ajá. What is the azimuthal number meaning? It's the shape. Okay? If you
Le
see
ponen un nombre tan difícil, pero ese
the shape,
parece una
El ship, Organic chemistry crossover.
shape.
No.
Bro. Ah, es que sí hizo trans. No,
Fernando,
it's
que el
Hillary.
productor no sé.
Ajá, el profesor Hillary.
Ay, sí, es cierto, lo otra.
¿Saben cómo le hace la
Ajá, ahora cuánto numeralia.
So,
Numeralia.
this that you see here. So, this one shows the different shapes it can have. And it depends if you are in the orbital S, P, D, or F. Now, how do I know those orbitals? If you go to the periodic table, the first 2 are in the orbital S. All of these from the group number 13 to the group 18, or group 3A, or 8A, or boron group, and noble gases, those are the P. The transition metals are going to be your group D, and your rare earths are going to be your group F. If you want to see it, here they are. S, P, D, and F. Now, there's a logic for this. Okay, so here you have to start to see that S can only have 2 electrons. Why? Because here you can only have 2 rows. Then P can have 6. Why?
6.
Because here you can have 1, 2, 3, 4, 5, and 6. Then D, you can have 10. Why? Because here from 3 to 12 you have 10. And finally F, you can have 14. There's another one which is H, but there are, o sea, ya está teorizado, pero no hemos encontrado los electrones. Which are the rare earths? If you count from 57 to 70, those are going to be 14. So, if I were to tell you to give me the electron configuration of the boundless electron, aquí está como que... Si yo les pregunto que me den la configuración, no la configuración electrónica, me quiero que me den el número cuántico del electrón de valencia de la plata, bueno, ¿qué es lo que yo hago? La plata está en el 47, ¿va? Pero está en el sector D. Entonces yo sé que, por ejemplo, AG47 va a ser D algo. Ahora, ¿en qué número está cayendo? 1, 2, 3, 4, 5, 6, 7, 8, 9. Está en la fila 9, entonces va a ser D9. Y ahora, ¿Por qué se está ordenando así? Porque recuerden que es N. Bueno, no, ahorita se puede explicar. Ahora, ¿qué me falta aquí? Me falta el tamaño. Ajá. ¿En qué tamaño cayó? Está aquí a este lado, está en el número 5. Pero son metales de transición. Los metales de transición en verdad van uno más abajo.
Sí.
En términos reales sería uno más arriba, ¿no? Ajá. Entonces sería 4 de 9. Ese es el número, el número cuántico del electrón de valencia de la plata.
Todo no
Y de ahí se puede sacar todo lo demás. Ahorita voy a eso. Me quedé en la L, malo.
Los Ds son los que...
Sí, y también F. La explicación más rápida es porque hay algo que se llama el principio de Aufbau.
Ah, sí.
Aufbau. ¿Qué es el principio de Aufbau? Yo le digo de cariño el árbol de Navidad. Para que sea festivo.
1 es 2, luego 1D.
Exacto.
Entonces,
quedamos que ¿cuántos tenemos? 7 periodos. 1, 2, 3, 4, 5, 6, 7. Y esos van a ser S. Ahora, para que esto sea más sencillo, voy a agregarle el octavo, que es el que se ha estado utilizando desde los años 80, para que esto cumpla. A partir de aquí, ¿qué es lo que voy a hacer? Como pirámide le voy a ir quitando 1 y 1. Entonces, aquí voy a tener 2, 3, 4, 5, 6 y 7. Y estos van a ser P. Quito otros 2 y voy a tener 3, 4, 5, 6 y 7. Y estos van a ser D.
Ah, sí, porque es 8.
Y quito otros 2. ¿Qué pasa? Ya está 6. Entonces, ¿qué? 4. Quito 2. Voy quitando 2. Quito otros 2 y me voy a quedar 4 y 5 F. Ahora, vamos a ver un poquito la tabla periódica. La tabla periódica, esto de lantano y actinio es como una tubería de Mario Bros. Que debería estar aquí.
Sí.
Están aquí. Entonces, este a fuerzas va a caer en 4 y el otro va a caer a fuerzas en 5. Aquí tengo 4 y 5. No, tengo 6 y 7. Significa que tengo 2 menos. Tengo que, o sea que a lo que si yo veo algo aquí, automáticamente, bueno, con la F es más sencillo porque solo hay 2, no es como cajetear. La primera es 4 y la otra es 5. Con la D es en donde la gente se me cuatripea. ¿Por qué? ¿Dónde inicia la D? En 3. Los metales de transición inician en el 4. Entonces significa que estos son 3, o sea que es 1 menos de lo que vale el número del periodo. Este es 3, este es 4, este es 5 y este es 6. Entonces este estaba en el 5, por eso es que es 4. ¿Ok? Eso se llama electron rearrangement. Es no confundir con el electron rearrangement de orgánica. Eso es otra cosa, que es de por qué el enlace doble y el OH se convierten en un ketón. Eso es otro tipo de electron rearrangement, pero eso es un rearreglo de electrones cuántico. ¿Ok? ¿Dudas?
Entonces era 5s2 y luego ponemos el double gas.
Sí. Ok, entonces tenemos N, L, falta M y S. M,
¿Me puedo bajar tantito?
búscalo como principio de Aufbau. De hecho, ¿no está en su bucle?
No.
no, eso no.
Ya saben cómo hacerlo, más sencillo. Ajá.
Pero el 8 sí está.
Es teórico, no existe. En la tabla periódica no está, pero es teórico.
Pero
Por ejemplo, neodimio, fluoridio, foscorio, dicarbonio, tenesio y magnesio no existen.
No,
No,
el
del
H, ¿verdad?
No tiene
No.
elementos que lleguen al 8.
¿cómo existe?
Profe, ¿cómo que no existen?
No existen, son teóricos. O sea, ya se descubrieron, se pudieron sintetizar, pero se tiene sintetizada son microgramas. No existen. De hecho, si me voy más cañón, el astato tampoco existe. Y está
Esos-
arriba.
Esos son los que los hacen en el acelerador de partículas, ¿no? Y los se destruyen.
Porque es muy inestable.
Son inestables, entonces son teóricos. 5 minutos.
Pero tenemos
Pero
la otra hora,
tenemos la
profe.
siguiente.
Tenemos la siguiente
Va.
hora.
M, magnético. Es número cuántico magnético. ¿Qué es lo que me dice? El número cuántico magnético me dice si los electrones, o sea, por ejemplo, aquí el 4D. 4D significa que, o sea, D significa que tiene una forma como que sí. Pero como es 4D significa que tiene una forma como que sí. Si mi magnético es positivo, significa que está de aquí para arriba. Si está negativo, es de aquí para abajo. Ajá. Entonces me está diciendo la polaridad en la cual de toda la estructura yo voy a encontrar ese electrón. O sea, este electrón, supongamos el 4 de 9, me está diciendo que es el noveno electrón. Entonces, ¿cómo lo voy a hacer? No, sí, si lo vemos en el otro salón. Vamos a ir moviendo.
Es de que
primero
tienes los positivos y luego los negativos.